A very good time to you people. So now in the last session we have discussed about the difference between combination logic circuit and as well as your sequential logic circuit. In this session we are going to discuss about in the last session itself we have discussed about what is a flip-flop. A flip-flop is basically an memory element or a storage element which is used to store a bit of data. So there are different types of flip-flops, of which the four types that we are studying is your set reset flip-flop, which is called as your SR, and the next type is called as your JK flip-flop, and third one is called as your D flip-flop, and the fourth one is called as your T flip-flop, of which the flip-flop of our current study is your SR flip-flop, which is called as your set reset flip-flop. So first of all, before going to this, we need to know what is a flip-flop is. It's basically an 1-bit memory cell, and its output are your Q and Q bar, Q and Q dash or Q and Q bar, which are always complementary to each other. The circuit has two stable states. If Q is equal to 1, okay, if Q is equal to 1, it is a set state. If Q is equal to 0, it is called as your reset state. If the circuit is in any one of the state, it will continue to remain in the state. Say for example, if it is in set state, it will try to remain in the same state. If it is say for example Q is equal to 1, it is called as your reset state, it will remain in the same state. So if the circuit is in any one of state, it continues to remain in this state. This property is referred to as the memory property. And as of flip-flops, the two inputs are designed as your set and as well as your reset, because S is equal to 1. S is equal to 1 brings the circuit in set state, and R is equal to 1 brings the circuit to the reset state. If both are equal to 1, then both the outputs will try to become as 1, which is not allowed. So only that is called as your indeterminate state. When S is equal to 1 and R is equal to 1, that state is called as an indeterminate state. We can't maintain that state. So as of set and reset flip-flop, SR flip-flop is about when 0 and 0, it is okay, it is called as your memory state or no change state. When your S is 0 and as well as your R is 0, set is 0 means your Q is equal to 0. When your set is 1, R is 0 means your Q is equal to 1. Okay, if you know the Q, then Q bar or Q dash is the complementary of the Q. But with both the input are equal to 1, set and as well as reset, both are 1, then your output cannot be determined. There is no completely designated output as of your S and R, both are equal to 1. So now we can see this is called as a clocked SR flip-flop. So if you have a clock, okay, we are using 4 NAND gauge to implement this. So if you use a clock for the G3 and G4, this is called as a SR flip-flop. Instead, if we use an enable signal, okay, enable signal between this G3 and G4, then that is called as an SR latch. Okay, so now we are going to see about the clocked SR flip-flop. So here Q and Q bar are your output, and this Qn plus 1 is the output state, next state output. Say for example, if your Q is equal to 0, S is equal to S is equal to 0 and R is equal to 0, then your Qn plus 1 is equal to Qn. Qn means, which is called as your Qn plus 1, and Qn means Qn plus 1 output is your Qn means, which is called as a previous state of your Qn plus 1. Previous state of Qn plus 1 is called as your Qn. Okay, the previous state of your Qn plus 1 is called as your Qn. Now what we can do is, so only this S and R are 0 and 0. This is called as your no change state. This is called as your no change state. If your S is equal to 1 and R is equal to 0, then your output will be equal to 1. Now the flip-flop is said to be in set state. When your S is equal to 0 and R is equal to 1, now you can say the flip-flop is in reset state. When both are equal to 1, we can say that it is an indeterminate state. As the name itself instincts, clocked SR flip-flop. Clocked means we need a clock signal, right? When your clock is equal to 0, so if it is 1 means it is called as there are two types of clocks. One is called as a positive edge clock, and next one is called as a negative edge clock. Let me take this to be granted as your positive edge clock means when your clock signal is 0, whatever the input of your SNR, there won't be any change. But whereas when your clock is asserted as 1, so now depending on the change in the SNR, your output will also change. This is called as your next state of Q. Okay, when your input is 0 and 0, your output is no change. This state is called as your memory state. No change means whatsoever the output that was published previous, the same output will get remained when your S and R both are 0 and 0. Okay, but whereas when your S is equal to 0 and R is equal to 1, when your S is equal to 0 and R is equal to 1, your output is equal to 0. This state is called as your reset is 1, right? This state is called as your reset state. But whereas your S is equal to 1 and R is equal to 0, this state is called as your Q is equal to 1. This state is your set state. When S and R both are 1 and 1, indeterminate state. Indeterminate means we can't give a speculation, okay, of what will come at the output. But whereas of all the three stages, the before three stages, we can give it as this is the desired output you will get at the output. But whereas as of 1 and 1, okay, you can't define any output. Now when the power is switched on, so this is a clocked SR flip-flop, right? Instead of this clock, if you have an enable, what will happen? You will get the, okay, it is called as a SR latch. Okay, when the power is switched on, the state of the flip-flop is ascertained. Direct asynchronous, okay, direct asynchronous input presents, which is called input preset, and clear CR can be used to initially reset or to set the flip-flop. See, for example, we are having four types of, okay, four input combinations, right? So the first combination number one is called as your combination number one can be set to be your 0 and 0, and the combination number two can be set to be your, the combination number two is called as your 0 1, and the combination number three is called as your 1 0, and the combination number four is called as your 1 and 1. Okay, so totally you are having four NAND gates, G1, G1, G2, G3 and G4. This coupling is called as your cross coupling. From the output input to the input, a signal has been fed in. Okay, so we have told that as of sequential circuit is about, there will be a feedback from the output to input, right? So output from the output, a feedback has been given here. So this is your preset and clear pins which is given to your G1 and G2, and for your G3, your SNR, your truth table inputs, SNR will come. This is called as the internal diagram using a NAND implementation. You can implement this with the help of your NOR gate or two. So this is the logic diagram or the block diagram. So SR flip-flop. So your SNR your inputs. This is your clock input, clear, preset, Q and Q bar. Okay. Now let me come. This table has more information about your SNR flip-flop. So this is called as your logic diagram, your clock signal, your SNR, Q and Q bar. Now this is your characteristic table. How to derive this characteristic table is we know that it can have the input as 0 0 0 1 1 0, and 1 1 is not at all needed because it is a redundancy stage. It's an indeterminate state. So you take your, to get the output Q next, what are the things you need is you need your SNR input, and apart from that this Q is also needed. This Q is needed. Okay, so S, R and Q you take, and this Q next is the next thing we are going to find. Since the inputs are 3 in number, you can write from your 000 to 111. Now the Q next can be, now you take your S, R and Q 0 0 and 0. Your S is 0 and your R is 0 and your Q is taken as your 0. Now what you could do is, when your S is 0 means when it is passed through a NAND gate, it will become as 1. Okay, it will become as 1. When your R is 0, when it is given to an NAND gate, the output is called as your 1. And your Q output is equal to 0, right? Your Q output is 0. Okay, your S is given as 0 and R is given as 0. So your output here is your 1 and 1. See, say your clock signal we have given it as 1. So 0 into 1 is your 0. That is taken inverter means that is called as your 1. And NAND gate, for NAND gate when you give 0 and 1 means your output will be 1. And for this this NAND gate also 0 and 1 is given means your output is called as your 1. Now your Q is equal to 0. Your Q is equal to 0. Take this Q here. Take this Q here. So now here 1 and this is 0. This Q is coming as 0. 1 and 0. Okay, 1 and 0 is there. If you take this 1 and 0, okay, if you take this 1 and 0, 1 and 0 when it's given to a NAND gate, it will become as your 1. It will become as your 1. Now you take this 1 to here. Okay, now already here 1 is there. Okay, now already here 1 is there. Okay, this 1 will again come. So 1 and 1 is called as your, when it's given to a NAND gate, it will become as 0. So your Q next is equal to 0. Your Q next is equal to 0. Next you come for the next input, which is called as your 0 0 1. Your S and R are 0 and 0, and your output is equal to 1. When the input 0 and 0 is given, means here it will be 1 and 1. Now you take the Q input as 1. That input will come here. So here 1 and here also 1. 1 and 1 is the input to this NAND gate. So when 1 and 1 is multiplied, okay, when 1 and 1 is given to this NAND gate, the output is equal to 0. Now you take this 0 to this NAND gate, here already 1 is there and this 0 will join. When the two inputs are different, okay, your output will become equal to 1. So you have got this one right. Like this, you can complete this characteristic truth table. I will explain the second alone again. Your input is S and R are 0 and 0. When it's given as S and R are 0 and 0, your NAND gate output will be 1 and 1. Okay, your NAND gate output will be 1 and 1. And next, what you can do is, your Q is called as your 1, right? Your Q is 1 here. So that 1 will be taken here. Okay, this 1, already 1 is here. And this is another 1. When two inputs are same 1 and 1, your output is equal to 0, okay, for out of a NAND gate, and that 0 will be taken here. Okay, this 1 along with 0, okay, 1 and 0 is given a here input, means then your output is equal to 1. Like this, you want to fill these combinations, you want to fill totally 8 combinations, you want to fill up to your 6 combinations only, because 1 and 1 is an indeterminate state, right? You don't want to fill, okay, you keep it as and don't care. Okay, up to 6 states you fill, up to 6 states. Say for example, let me take the 6th state as 1011, right? So 1 0 and this here it is your 1. When 1 and 0 are given input, means this will become as 0 and 1. This is your 0 and this is your 1, and here 1, right? So here 1 is there, that 1 will be taken here. Now here this is your 1, this is your 1, and this 0 has been changed to 1, right? So that 1 and 1 will become as 1 and 1 will become as your output is equal to 0, and that 0 is taken here and that 0 is taken here. Okay, when that 0 is taken here again, okay, you will be getting this your 1 is given here and that will become as your 0, right? So 1 and as well as your 0, both inputs are different, so your output is equal to 1. So only you are getting dash 1. Sir, it's simple that you want to give your S and R the inputs, okay, and as well as your output, you fix this output, okay, and then when you give a NAND gate input to a NAND gate, that will be just getting what to say extrovertly, it will become as your negated output. You will get here your negated output, you will get here. Use this value, first compute this, okay, first compute this, first I will tell you the protocol. First compute this, and this output will be taken and given to this G1, and finally you compute this. That is, first compute the values of G3 and G4 with the help of your SNR, and using the value of your Q, compute the value of your G2, take this value of your G2 and give to your G1 to get the output, final output Q. Now how to draw this excitation table is with the help of your Q and Q next you can draw. So Q and Q next means this your 0 0, okay, two inputs, right? 0 0 0 1 1 0 and 1 1. Now what you can do is, here for 0 0 your SNR is 0 0, again here for 0 0 you are getting the 0 1, two difference, okay. So what you can do is, for the 0 0, for 0 0 you are getting 0 0 and as well as your 0 1. So that 0 is retained, so you put it 0, and here your R is varied from here 0 to 1, right? 0 to 1 transition is there, so you put it as your X, okay. And for your 0 1 and for your 0 1, you can take this, when your input is 0, when your inputs are 0 and 1, your output is equal to 1 0, okay. And when it's for your 1 0, your output is called as your 0 1, your output is called as your 0 1. When it is for your 1 1, okay, here 1 1 it's your 1 0, and here for 1 1 it's called as your 0 0. That means 0 is retained, so 0 here it is placed, but whereas your S input is varied as your 0 to 1 transition, which is called as your X. So such that you have from the symbol you have drawn the characteristic table with the help of this NAND implementation, and finally excitation table has also been derived. This is called as a state diagram. When you go for problems using your state machine diagrams and all, you need to know this. how to deduce this is, so q is equal to 0 and q is equal to 1, q is equal to 0 and q is equal to 1. Okay, so what are the, for what are the outputs is giving us 0 and what are the outputs is giving us 1, that's what given here. So for example, if your S and R are 0 and 0, your when your S and R are your 0 and 0, okay, S and R are 0 and 0, it can be retained on the same state, okay, it can be retained on the same state, or it can be directed to your next state also, or it can be directed to from your 0 0, it can go to the next state also. Okay, for your 1 0, okay, for your SNR to be your 1 0, for your SNR to be your 1 0, it can go to the next state also, it can go to the next state also. And here also your q is equal to 1 means q at the q is equal to 1 state, your SNR is equal to 0 and 0 means 0 and 0 means what it implies is SNR is equal to SR is equal to 0 0 means no change, it can retain in the same state, it can retain in the same state, or okay, that is, or else if your SR becomes your 0 1, it will go to this next state. See, S and R 0 0 means no change, okay, no change will occur on both sides. When your SR value is your 0 1, it will be on the same state because first bit is your S set, right? Set is 0 means it will be on the same 0 state. Okay, if your SNR is equal to 1 and 0 means it is going to the next state, which is called as your Q is equal to 1. Like this state diagram could be assigned, and this is called as your what to say, your Q next uh, characteristic equation. How to write the characteristic equation is use the three variable k map. Okay, for what are the inputs you are getting 1. Okay, for this input you are getting 1, for this input, for this input, okay, these three inputs, right? You put it in the k map and you can find the q next is equal to s plus r dash into q. That's what about the characteristic table and excitation table. Okay, so I will give you a session for keeping okay, how to proliferate this excitation table in the memory. Okay, the state diagram I think you all will be clear. The thing is 0 and 0 is the previous state, that is called as a memory state. 0 and 1 is called as your 0 and 1 is called as your reset state. 1 and 0 is called as your set state, and 1 and 1 is called as your indeterminate state. Thanks for listening. Thank you.